Hi, my name is Jason Beck. I work for Flowcorp, and we're a company that specializes in flow, level, and display. Today I want to take a couple minutes and explain the difference between two technologies that are on the market right now for measuring level. The first one we're going to talk about is ultrasonic, and the second we're going to talk about is radar, and specifically guided wave radar. So let's check it out. The first thing that's helpful to understand is a little bit of the science behind how these two technologies work. Starting with ultrasonic level meters, essentially ultrasonic level meters use ultrasonic sound energy. And that sound energy is created inside the driver the same way we would think of like striking a bell. So you strike the bell and then the sound waves will travel away from the driver. And I'll talk in a second about how that actually creates a measurement for us. Radar uses microwaves, and so this works a little more like a cell phone. There's no actual moving parts to create the microwaves, but it's a solid state device. Another difference between the two is ultrasonic sound energy travels at about 340 meters per second, whereas microwaves travel at just under 300 million meters per second. So microwaves travel far faster. What this means for us is that an ultrasonic level device can take one reading every 2 to 5 seconds, whereas a radar level device takes 70 readings per second. There's a principle called time of flight that both ultrasonic level meters and radar level meters operate on. Time of flight would tell us that if we send a signal from the driver to the surface of whatever we're measuring and it returns, we can then divide that in half to get the time for the signal to travel one way. Once we have the time that the signal takes to travel one way, we can get a level calculation out of that. Okay, I want to take a minute to show you an example of each of these devices. First, I want to show you an ultrasonic level transducer, which this is an example of that. Essentially, the driver is on the bottom here, and the ultrasonic sound energy is transmitted from the driver down to the surface of what we're measuring, and using time of flight, which we just talked about, it will return, and that's how we get our level calculation. This is an example of a radar level meter, and specifically this is a guided wave radar level meter, which is what we're comparing in this tutorial. Essentially, this works in a similar way to the ultrasonic transducer. The microwaves are sent through the feed-through, down the probe, and then the return signal comes up, and that's how we get a level calculation. This is also a good time to talk about contacting versus non-contacting level meters. The ultrasonic transducer we saw is a non-contacting level meter. Essentially, there's no physical hardware parts in the media that you're measuring. The difference here with the guided wave radar is we do have the probe inside of the media that we're measuring. So even though in both cases the sound energy of the ultrasonic will touch the surface of the water, because there's no actual hardware inside of what you're measuring, it's considered non-contacting. Because the probe extends through the liquid that you're measuring, it is considered a contacting meter. While the science and technology behind all this stuff may be interesting to you, you're probably much more interested in how this actually works in a process application. So I'm going to walk us through 4 examples, and we'll use the whiteboard and show some examples in tanks of the difference between how an ultrasonic transducer and a radar level meter would differ. The first process application we're going to look at is pretty ideal. The liquid isn't turbulent or sticky or anything like that, and it's pretty ideal process condition. So let's take a look at how these two meters work. Starting first with the ultrasonic, we're going to see how the sound energy is sent down to the liquid surface. It will echo and return back up to the transducer, and that's how we'll take our measurement. Okay, so it'll strike the surface of the liquid and then return. And and then we'll use time of flight here. Essentially the device would be programmed to understand this is how long it took two ways, and then it'll calculate the time for one way, and then it'll take a level measurement based off of that. Guided wave radar works a little differently. The signal will come out in a circular pattern from the probe, kind of like if you threw a rock in a pond or something, the ripples kind of straight out. That's the idea behind how radar measures. So it's going to measure more in a circular pattern here. And it will take that measurement all the way down to the bottom of the probe. And again, this is happening at 70 times per second, whereas this is taking one measurement every 2 to 5 seconds. So how the radar works is it's taking all these measurements. When it finally gets into the liquid here, it will take a measurement and continue to do that. And so the artificial intelligence in the meter up here, when it receives this return signal, will know that this is the liquid measurement because it's where it first got a good full signal, and then it confirmed that there isn't a greater signal anywhere below it. So actually both of these meters will work pretty well in this situation. You're going to get a little bit of reflection and echoes off the sidewalls of your tank, but nothing that the ultrasonic level meter can't handle, and the radar is very well suited to be in this environment as well. The second process condition I want to talk about is a situation where there would be turbulent liquid. So maybe you have a pump running in the tank, or there's an inlet that's coming in at a pretty good velocity, and whatever the circumstances are, your liquid has a fair amount of waves and turbulence going on. So let's take a look at the ultrasonic transducer and see how it measures in this situation first. So essentially the signal will come down. And it will strike the surface of the liquid we're measuring, and then we're going to get some interesting echoes here. We're going to get some that come straight back up just based on how the turbulence is happening. But what becomes problematic in this situation is we're going to get some other echoes. We're going to get some coming off this direction and this direction. And essentially it's going to bounce off the sides of the tank. And what we're going to get up here is just echoes coming in from every direction. Now, ultrasonic level meters are designed with some algorithms that they should factor some of this stuff out, but this can give you a problematic reading. This is one situation where radar becomes a little superior to the ultrasonic. The way it measures in this situation, again using circular measurements out from the probe, okay, so when it hits here, it is going to take a measurement. It's going to say, okay, there's some liquid. It's going to realize there's some liquid here. It's going to take a measurement. Even more still. And when it gets right here, it's finally going to take the strongest signal so far. But the benefit here is it continues on to the bottom of the probe. And so it confirms, okay, that was the strongest signal. That is definitely where the level of the liquid is. So the signal returns straight up through the probe, so there's no reflection off the side walls of the tank that are problematic the same way that is problematic for ultrasonic. The third process condition I want to talk about is foam. How does ultrasonic respond compared to guided wave radar in foam? So we'll take a look here. The ultrasonic meter sends a signal, and when it hits the surface of the foam, the problem is with ultrasonic sound energy is that it's absorbed by foam. So most of the signal will disappear here. We'll probably get a small return of some sort. So that may take a level measurement, or the ultrasonic transducer may factor it out and reason that the signal wasn't strong enough, so it must not be the actual level of this liquid we're trying to measure. All right, so radar, how does that compare? Because radar uses microwaves, it can't really pick up foam the same way it does a liquid or something. So even though it takes a measurement here, it doesn't recognize it as the surface of the liquid you're trying to measure. It continues down. It's going to start taking measurements here. I mean, it takes measurements all the way down, but what I mean is it's going to start reading actually that it's in the liquid, or it's taking a real measurement. And it'll continue on down to the bottom of the probe. Essentially, it's going to take this strongest signal here when it first gets into the liquid. It's going to ignore the foam, and we're going to get an accurate measurement. So guided wave radar becomes very ideal in a situation with foam where ultrasonic really cannot cut it. The final process condition I want to talk about is a situation where there would be an emulsion on the probe. This only really applies to guided wave radar as it is a contacting level device. But we'll get a question sometimes about, well, what if I have a really sticky liquid that as the level comes up and down, I start to get an emulsion buildup on the probe. Will it accurately measure in this situation? Well, we'll talk about this. It will. The Tracer 1000, which is our guided wave radar, will work properly in this situation. I think most guided wave radar should be fine. I know ours will definitely work in this situation, and this is why. All right, it starts measuring here, and it will take a measurement. It'll keep taking measurements, so it's recognizing there is some sort of substance here on the probe. When it finally gets into the level of the liquid, once again, it takes the accurate measurement. So emulsions are no problem because the microwaves extend in circular format out from the probe, and essentially it can factor out the emulsion because it realizes it's not the strongest and most complete signal. Because it measures all the way to the bottom of the probe, it will actually get to the real liquid and translate that appropriate signal strength properly. And when it sends the signal back up into the meter, the artificial intelligence will properly calculate where the liquid level is. So emulsions are not actually a problem for some and probably most guided wave radar units. Well, that's the end of this tutorial. Again, this is our guided wave radar meter. It's called the Tracer 1000 for liquids, the Tracer 2000 for solids. I hope you check out our website if you want more information, and really if you need anything for flow, level, or display, we'd love to help you out. So check out the website if you get a chance. And again, my name's Jason. Thank you for watching this tutorial.